Okay, good morning, everyone. So we are going to just do one. I want to talk a little bit about this last problem that we were doing from the comparison test. We were doing a limit comparison test. And I said, just in the scratch work or thinking process, if I look at 1/2 to the n, and that should be -1, not in the exponent. Let me rewrite that. That -1 should be down here. Then as n gets really large, 2 to the n gets very large, and it just looks like 1/2 to the n. So we are going to have an is 1/2 to the n -1, and bn, we said by just our thought process, is that. So therefore, we're going to look at the limit as n approaches infinity of an over bn. Okay, so where did that theorem start here? Here was our theorem. Look at the limit as n approaches infinity to a of an divided by bn. And if we get a number, any number L, any number, then they both converge or both diverge. So let's look at this. So this becomes the limit as n approaches infinity. When I divide an by bn, I'm going to get 2 to the n in the numerator divided by 2 to the n -1. And as n goes to infinity, 2 to the n goes to infinity. And as n goes to infinity, 2 to the n goes to infinity, 2 to the n -1 goes to infinity. So therefore, what rule am I going to use in order to complete this limit? Anybody have an idea? What rule?
L'Hopital's.
Awesome. So I'm going to use L'Hopital's rule, and L'Hopital's rule says take the limit as n approaches infinity of the derivative of the numerator. What is the derivative of 2 to the n? Oh, we're pulling out some ancient stones here in order to do this. We learned this way back. How do you take the derivative of 2 to the n? Anybody remember? Okay, I assume you guys are frantic looking through your notes. What is it, Caesar?
I'm just guessing here. Would it be 2n minus? No, wait. 2n n -1.
Okay, actually, we cannot take the derivative like that, but you're on the right track. 2 to the n is part of the answer, but then we have to take the natural log of 2. And the derivative gives us 2 to the n, natural log of 2. So that's the limit as n approaches infinity. And that just is 1. So that just is equal to 1. Okay, so therefore both series converge or both series diverge. Okay, so that means we need to look at our summation bn. So that's the summation n equals 1 to infinity of 1/2 to the n. Okay, so how can we determine whether or not this series converges or diverges? What does it look like? It kind of has a certain form. What does it look like?
So 1/2n?
Yes.
It looks like the P series.
Okay, actually, that is also a good guess, but that's where we get tripped up just a little bit. Remember, the P series is the summation of 1 over n to the P. So n is the base in the P series. Here I have 2 as the base. And a lot of students think that that's a P. I agree with you that that's what it looks like. But actually, you rewrite this as the sum n equals 1 to infinity. And if I make it 1/2 to the n, does it start to look like anything else that we know?
That isn't trig, correct?
Say that
Trig.
again.
Is it the well, I forgot the name already. Trig? No. Geometric series?
Yes, this is a geometric series. Okay, so we know our geometric series to start summation n to the 1 to the infinity of 1/2 to the n minus 1, right? We know that that's what it normally looks like. All right, so the series on the left starts with 1/2, where the series on the right starts with n being 1, which would give you the first term being 1. Okay, so therefore this series looks like that series. But this converges. It's a geometric series. A is 1, R is 1/2. The absolute value of R is less than 1, so therefore it converges. All right, so that then implies this converges. And then that implies by the limit comparison test, the summation n equals 1 to infinity of 1 over 2 to the n minus 1 also converges. Okay, so once you show that its Bn converges, which we just did, then we know the summation An converges. Okay, so that's the end of our limit comparison test. That was our last example. And so now we are going to move on to our alternating series test. Okay, so the alternating series test, we are going to do the following in this section. Use the alternating series test to test an alternating series for convergence, estimate the sum of an alternating series, and explain the meaning of absolute convergence and conditional convergence. So we're going to do all of that in this section. So as we do with every section, we're going to go back and just do a little review of the series test that we have looked at. We've looked at the geometric series test, the telescoping series test, the nth term test of divergence, the integral test, the P-series test, the direct comparison test, and the limit comparison test. And now we are using the alternating series. Okay, just a few questions. Which test actually can provide you the sum of the series if it's convergent? Which test can actually provide the sum of the series if the series is convergent? I'll give you a hint. There are 2 of them.
Is there telescoping?
Telescoping is one, and what's the other?
Geometric?
Geometric.
Oh,
Awesome. Okay, which of these series cannot tell you if a series converges?
Is it the nth term test?
The nth term test of convergence, divergence. Does not tell you whether the series converges, it only tells you if the series converges. Okay, which of these tests do I have to make my series smaller than a convergent series or bigger than a divergent series? I'll say it again. Which of these tests do I need to bound my series being smaller than a convergent series or bigger or larger than a divergent series?
Would
that
that
the
be the
direct
P
comparison?
series?
Say that again.
I think
I
we
had-
both spoke at the same time, but I said the direct comparison test.
Okay, so it is the direct comparison test. You are comparing your series with another. So it is a direct comparison test. Okay, which of these series is in a specific form that if the exponent is greater than 1, it will converge?
Would that be the P series?
That is the P series. Okay. All right, so we're going to go straight into the alternating series. I'll have some questions for you again. All righty, so here is the alternating series. So I'm going to give you an example first of what an alternating series looks like. Okay, so here is an alternating series. An alternating series will have -1 to the n plus 1. You may see -1 to the n, and you may also see -1 or -1 to the n plus 1. Okay, so you may see n plus 1, n, or n minus 1 as an exponent. Either way, the terms are alternating between positive, negative, positive, negative. So -1 to the n plus 1 divided by n, the first term you put in n equals 1 and you get -1 squared, so that term will be positive. The second term you put in n equals 2, so I get a 2 in the denominator, -1 cubed, which will make it negative. The next term I get a 3 in the denominator. I'm going to get -1 to the 3 plus 1, which is -1 to the 4th, so that's positive. So this is an alternating series. The next one is also an alternating series. The summation, -1 to the n plus 1 of 2 to the n minus 1. So the denominators are going to go as 2 to the 0, which is 1, 2 to the first, 2 to the 2 squared, 2 cubed, etc. And the numerators are going to be forms of -1 or +1, and they are going to alternate back and forth. Any questions about that? Okay. All right, so alternating series have a certain form. All right, so the form is a -1 to the n plus 1. And as I said, that could be a n minus 1, or it could be an n, just as long as it alternates back and forth. And then the rest of the series is called un. Okay, so if we go back just a minute, in this series here, un is the 1 over n part. Okay, everything else is -1 to the n, so un is 1 over n. And in this series, un turns out to be 1 over 2 to the n minus 1. So you're going to need to be able to identify what un is. Okay, so alternating series are of the form -1 to the n plus 1 times un. So you will get u1 minus u2 plus u3 minus u4. or it may start off -1, negative U1 plus U2, negative U3. Either way, it alternates in sign from positive to negative. So we have a alternating series test. And this test, we can determine that this series converges if the following 3 conditions are met. So the first condition is that the UN must be positive. The second condition is UN has to be larger than UN plus 1. In other words, UN plus 1 is smaller than the one before it. So the terms are getting smaller or they are decreasing. And the last is that the limit as n approaches infinity of UN has to be 0. Any questions on what the alternating series test requires us to do? There are 3 steps. Okay. First example. All right, so we have the summation of -1 to the n plus 1 over n. All right, so we already said what this series looks like. We identified that UN is equal to 1 over n. All right, so the first part of the test is we need to show that UN is greater than 0. Okay, well, let's see. For this one, it's rather easy. We have UN is equal to 1 over n. And if this is greater than 0, we can multiply both sides by n. We know n is positive since n is greater than 1. Well, it's greater than or equal to 1, which is greater than 0. So n is positive, so I can multiply both sides and I get 1 is greater than 0, and that is a true statement. So we are good on the first condition. The UN is indeed positive. The second condition, we need to show that UN is larger than UN plus 1. Okay. All right, well, let's do that. We have UN is 1 over n, and UN plus 1 is 1 over n plus 1. All righty. So therefore, UN being larger than UN plus 1, well, that would mean 1 over n has to be larger than 1 over n plus 1. And we know that n, again, is greater than or equal to 1, which is greater than 0. So we can multiply, so we get n plus 1 is greater than n, so I get 1 is greater than 0. And again, this is a true statement. Okay, now there is another way to show this. So the alternative is that given UN is equal to 1 over n, we can make a function of it, ux, fx would be 1 over x, and show that show f of x is a decreasing function. So we can show f of x is a decreasing function. So in calculus, what does that mean about the derivative? If f is a decreasing function, what do we know about its derivative? Wow. That is to show that f prime of x is less than 0 for big X, for large X. Okay, so f prime is -1 over x squared. And that's always less than 0 since x squared is positive. So f prime is a decreasing function. Because its derivative is negative. So that's going to imply that un has to be bigger than un plus 1. Okay. All right, so we've shown number 2, and then the last part is we need to show that the limit as n approaches infinity of un is actually 0. So if we take the limit as n approaches infinity of un, that is the limit as n approaches infinity of 1 over n. Oh, well, we already know that's 0. Okay, so we said that. So what have we shown? We've shown all 3 properties for this problem. Okay, the first thing was we showed un was positive. Then we showed un was always bigger than un plus 1 because we got a true statement, or we did the alternative derivative. And lastly, we had to show that the limit as n goes to infinity of un is actually 0. So we showed all 3 of those conditions. All right. Hence, A, B, and C imply the summation n equals 1 to infinity of -1 to the n plus 1 over n converges by the alternating series test. Okay, any questions about that? Okay, I'm going to stop for a minute and take the roll. Let's pause the video. Okay, so our next example is this series. And for this series, again, we need to identify what un is. So what is un in this series? Somebody tell me, what is un? What is un? Hello? Anybody present? What is un? I'll go back. So this is what our series looks like. We have -1 to the n plus 1, or n minus 1, or n. un is everything else. Okay, so un in this problem is what? Peyton,
N
what is
squared plus
un?
4.
Oh, thank you, Caesar. Wonderful.
Sorry.
Nope, I'm happy for the answer. What do you say? N squared plus 4.
over n squared plus 5.
Excellent. Okay. Thank you, Caesar. Okay, so that's UN. All right, so now we have to do A, B, and C. A says, let's look at UN and show it's positive. So we need to show UN is positive. Okay, well, we have here n squared plus 4 is positive, and n squared plus 5 is positive. So therefore, the ratio of two positive things is positive. So that implies UN is positive. Okay. Another way you could have done it is you could have taken UN equal to n squared plus 4 over n squared plus 5 greater than 0. N squared plus 5 is positive, so therefore n squared plus 4 greater than 0. So that says n squared is greater than -4, and that is clearly a true statement. Okay. B. B is usually going to be the most challenging part of this process. Okay, the most challenging. So even though they're written in this order, we can come back to that because usually part C is one of the most important and easiest parts, and that is to show that the limit as n approaches infinity of UN is 0. Okay. All righty. So therefore, when we take that, we do the limit as n approaches infinity of n squared plus 4 divided by n squared plus 5. And I would like you to please take the limit and tell me what you get.
Is it 1?
That limit is 1. Anybody else have a question about that? Anybody else have a question about that? Okay. So that limit is 1, which is not 0. All right, so the conditions of the alternating series test are not satisfied. Hence, we cannot conclude. That the series converges.
So once out of the 3 like don't work, you don't have to do.
One of the 3 doesn't work, you don't have to check the other one. So that's why I said I'm not going to spend any time doing number 2, which is the most challenging part, because number 3 does not work. So since number 3 doesn't work, I don't have to go back and do number 2. Okay, so I know that this series right here, I cannot conclude that it converges. I can't say it diverges, but the alternating series test says it will converge if those three things happen. It does not say it will diverge if one of them does not. Okay, so where am I? Here, sorry guys, I got a little lost. Okay, so we cannot conclude that this series converges. All right, let's look at our third example. Where is the example that I just had? I like that example. Yeah, I like this one a little better, but I'm gonna do the one that I have. All right, so here's our last series. All right. So what is UN?
10n over 2, oh wait, no, 10n over n squared plus 1.
All right, thank you. All righty. So we need to show UN is greater than 0. And so we get 10n over n squared plus 1. N squared plus 1 is positive. So we can multiply it without switching the signs. So that gives us 10n is greater than 0. We can divide by that. We get n is greater than 0. And that's a true statement because n starts at 1. Okay, so that's done. The second part we need to show that UN is bigger than UN plus 1. Okay, so now we've already shown that there are two ways to do this. All right, the first way is you can actually do the algebra, and that we did in this last problem, in problem number 1. So you can actually do the algebra, okay? Or a second way is to show that if you take the derivative, you get a negative number. So I like the derivative way. It's quick, fast, and it uses calculus. All right, so we're going to let f of x equal 10x divided by x squared plus 1. And I need to make sure it is 1, x squared plus 1. Okay, so we take f prime. We get the bottom, x squared plus 1 times the derivative of the top, which is 10, minus the top, which is 10x, times the derivative of the bottom, which is 2x, over the bottom squared. Okay. So that is, we have 10x squared plus 10 minus 20x squared divided by x plus 1 squared.
I just have a question. Shouldn't the denominator be x squared plus 1 since it's
X squared plus 1 squared. Thank you.
Okay.
Yes, yes, you are so correct. Thank you, thank you. Yay. You know, I did that to see if you were paying attention. Okay. So this is then equal to minus 10x squared plus 10 divided by x squared plus 1 squared. Factor out the 10, the negative 10, I get x squared minus 1 divided by x squared plus 1 squared. And that is less than 0, provided when x is bigger than 1. Okay, so for n bigger than 1, un is greater than un plus 1. And that's what we needed. Okay, so yes, it's true. And then part C, we need to show the limit as n approaches infinity of un is equal to 0. Somebody talk me through that, please. All right, I want somebody else to be the teacher for a moment. The limit as n approaches infinity of 10n over n squared plus 1. Somebody talk me through that.
Can I?
Yes.
So it would equal to infinity over infinity. Then you do L'Hopital's rule, which it would be 10 over 2n.
Good.
Which equals to 8n. No. 5n, my fault.
You mean 5 over n?
Oh, yes.
Okay, so now what happens as n goes to infinity? So remember I said, think about it as if you have 5 pizzas divided by an infinitely many number of people. How much pizza are you going to get?
Infinity?
You have only 5 pizzas. And everybody in the world is lined up for a slice. Peyton, come back. I saw you go away. Come back. You're gonna get this. How much pizza do you get if you have 5 little pizzas on the table and you have to divide it by infinitely many people? Let's say it's 10,000 people. How much pizza are you gonna get? Virtually.
Hold on, I'm confused. Sorry, there's too many numbers.
Okay, there's only 5 and there's n. That's it.
Okay.
So n is getting larger and larger and larger. Anytime there's an n in the denominator, okay, how about I write it like this? I think you might get it. 5 times the limit as n approaches infinity of 1 over n. Can you now, does that help?
Okay, so then it would be 5 times natural log of n.
Oh, whoa, no, we're not integrating. We're just taking this limit. Whenever n goes to infinity in the denominator, the whole thing goes to what?
I don't know.
Okay. This is a limit that you have to remember. The limit as n approaches infinity of 1 over n is always 0. Okay, that number gets smaller and smaller and smaller and smaller. So that is 0. Okay, so now we can conclude by A, B, and C the summation n equals 1 to infinity of, I'm trying to remember what it is, 10n, oh, no, there's an alternating part. Minus 1 to the n plus 1 times 10n over n plus 1 n squared plus 1 converges by the alternating series test. Okay. All righty, so we did 3 very strong alternating series test examples. So now we are to our next test. All right, so this is test number 9. So we're good. We only have 4 more, and we're doing 9 right now. All right, so test number 9. It is the test for absolute convergence. Okay, test number 9, the test for absolute convergence. It says a series, summation an, again, that's n equals 1 to infinity, converges absolutely if the corresponding series with absolute values converges. So that is, if you can show the summation of the absolute value of an converges, then the series converges absolutely. Okay, any questions? All right. I'll give you a moment to write that down. Okay, so of course we have examples. So here's our first example. So we're going to look at this series. Okay, so it is an alternating series. Okay, so we can use the alternating series test to show that this series converges. All right, so if you use the alternating series test, you can show, or you will show, this series converges. All right. Okay, so by using an alternating series test, that is A, B, and C, or parts 1, 2, and 3, showing that UN, which is 1 over n squared, so we already know what UN is. UN is 1 over n squared. That's positive. UN is greater than UN plus 1, and the limit goes to 0. So using the alternating series test, you will show this series converges. I'm going to skip that piece because that's something I'll give you to practice. All right, so you can practice that. Okay, so what I want to do is do the test for absolute convergence. All right, so here's the test for absolute convergence. So the test for absolute convergence says, let's look at, or we need to examine, the summation of the absolute value of the terms. That's the summation n equals 1 to infinity of the absolute value of minus 1 to the n over n squared. So that's just the sum, n equals 1 to infinity. When I take absolute values, I just get 1 over n squared. Now, what kind of series is that?
P-series.
It's a P series. Wonderful. This is a P series. What is P?
2.
P is equal to 2. So what does that tell me about this series?
It convergence.
Okay. All right. So this series is convergent because P, which equals 2, is greater than 1. Okay. So when I take the absolute value of the terms in the series and sum that, I end up getting a P series. And that P series converges. So summation AN, absolute value of AN converges. So that implies the summation of AN converges absolutely. And an absolutely convergent series is a convergent series. Okay, so now we can conclude that the summation n equals 1 to infinity of -1 to the n plus 1 divided by n squared converges absolutely. Okay. Any questions? All right. I don't have this as an example, but it just came to me. The summation n equal 1 to infinity of the sine of n over n to the fourth. Okay, so that series, I don't see -1 to the n, but it does alternate between -1 and minus negative, it does alternate. So I could, even though I haven't used the alternating series test, I can still look at the absolute value of this series. So using the absolute value, using the tests for absolute convergence, I can get the sum n equals 1 to infinity of the absolute value of the sine of n over n to the fourth. And that is equal to the sum n equals 1 to infinity of the absolute value of the sine of n divided by n to the fourth. Now, what do you know about the absolute value of sine? It's less than what number? Sine goes between what and what? Come on, y'all know this. Absolute value of the sine of any number is always less than or equal to 1. So this is less than or equal to the sum n equals 1 to infinity of 1 over n to the fourth. Okay, what do you know about that series? Quickly.
P series again.
Okay, so this is a P series. Not only that, it's a convergent P series, right? So what test am I now using to show that this converges? It's one of our previous tests. I have a series bound by a larger series that converges. What is that?
Is a harmonic series.
Oh no, this is not a harmonic series because I have n to the fourth.
Okay.
But we did a test that, thank you, Victor, for responding, because I know that people need to understand, that it's not a harmonic series unless it's just 1 over n. Okay, so I have a series Bn bigger than a series An, and the series Bn converges. What test am I using? We just did it.
So the comparison test.
Yay, okay. So by the direct comparison test, the summation n equals 1 to infinity of the absolute value of the sine of n over n to the 4th converges. So we showed that this converges by the direct comparison test. All right. And then by the test for absolute convergence, that implies that the summation n equals 1 to infinity, the one without the absolute values, converges absolutely. So I used 2 tests for this. I took the absolute value, showed that is less than something that converges. So I used the direct comparison test. And then I took that thing and said that because its absolute value converges, the original series converges absolutely. Okay. Of course, now we got one that was so beautiful. Let's go on to this one. So here's our next example. Again, you can use the test. So for this one, I have to use the alternating series test. All right. And what did I write before? I just want to be consistent. You will show this series converges. Okay, so if you used, when you use the alternating series test, you will show that this series converges. Okay, so now we need to use the test for absolute convergence. So now we need to examine the summation of the absolute value of an, which in our case is the summation n equals 1 to infinity. When I slap absolute values on there, I get 1 over n. And what happens? What do I know about this series? Victor, what kind of series is this?
This is a harmonic series.
Now that is the harmonic series. All right, you see it now? Okay, so
Yeah.
this is the harmonic series. Does the harmonic series converge or diverge? Does this series diverge or converge? We talked about this. We proved it with the integral test. This is the harmonic series. This is something you need to know. The harmonic series does what? What happens when you integrate 1 over x? What do you get?
That'll be the natural log of absolute value of x.
Natural log. And then what happens when you look at natural log as it goes to infinity? What do you get?
You get
The natural log. That function just. So the natural log as x goes to infinity goes to infinity. So that integral diverges, the series diverges. Okay, so now we can make a conclusion. Since summation of the absolute value of an diverges, the summation n equal 1 to infinity of -1 to the n over n does not converge absolutely. So it'll only converge absolutely if the summation of the absolute value converges, and this one does not. Okay, any questions?
What was the one condition again, which it could absolutely converge?
Okay, so it only absolutely converges when you put absolute values on it and look at to see if that series converges. So for this first one, we had the alternating series test. And when you do the alternating series test and check 1, 2, and 3, those 3 steps, or A, B, and C, whatever you want to call it, you will show this series converges. So now we're checking to see whether it converges absolutely. So it will converge absolutely if you slap absolute values on the AN term, the whole thing, and you look at the summation of just the UN part. So if you look at that and see if that series converges, then the original series converges absolutely. So for this one, I looked at the absolute value. I got summation 1 over n squared. That was a P series. It was convergent because it converged, which is the absolute value. Then the original series converges absolutely. But in the second example, I got the sine of n over n to the 4th. So now when I test for absolute convergence for this particular problem, I looked at the absolute value. I saw that the absolute value converged. This series converges by the direct comparison test. So therefore the original series, which did not have absolute values, converges absolutely. And then the last one I did was the only one that was different. I took and I looked at did the alternating series. You will show that it converges. But then when I did the test for absolute convergence and I put the absolute value gets rid of the -1 to the n, and it just gives me 1 over n. But this series diverges. So since the summation of absolute value an diverges, this series it converges, but it does not converge absolutely. Okay, so that series does not converge absolutely. So let me say, I'll even make it more clear. This series converges, whoops. By the alternating series test, but it is not absolutely convergent. Okay. Any questions? All righty. So the last test in this section. Uh-oh. This is test number 10. And this is the test for conditional convergence. And it's very simple. A series that converges but is not absolutely convergent is conditionally convergent. So that is exactly our last example. Okay, so in our last example, we did this example. So the first thing is we showed, I should put in parentheses because we didn't actually show it. I said you can show it by the alternating series test. That this series converges. Okay. We showed by the test absolute convergence that this series is not absolutely convergent. Hence, by the test this series is conditional convergent. Okay, so what did we say? Let's be clear here. So it says a series that is convergent. Okay, we showed by the alternating series test that this series convergence. Good. So a series that is convergent. We like that. But is not absolutely convergent. We showed by the test for absolute convergence, this series is not absolutely convergent. So it satisfies both criteria. Hence, it is conditionally convergent. Okay, so this is not absolutely convergent. So hence, it is conditionally convergent. Okay, I know this takes some time to digest. There is one more part of this, that alternating series test that we need to do, and that's the estimation theorem. We will do that on Thursday. In the meantime, I will post these notes, but just know that I'm going to repost them again if you, with the, I must change the file to the file that will include the alternating series test and the estimation theorem. Okay. That is it for today. Any questions?
Do you have office hours today?
I do, from 3 to 4.
Okay, thank you.
All righty. Okay, thank you. I will see you on Thursday, unless you come to office hours.